So there's 3 ways you can choose from A, big A, and there's 2 ways you can choose from big B. So the number of pairs will be 3 by 2. Okay, so 6. Okay, here's question 5. I'll skip 4. I've got to leave some for you to do. Okay? Let's just give you a feel. Question 5. So C, set C, big C, is a set with little c elements. How many elements are in the power set of C? Explain your answer. Power set of C. Well, you're trying to find a subset. And let's say, so here's your C, right? With all your elements in it. And here's the subset that you're forming. So this is your subset. Now, how many different subsets can you get? And that would be the size. How many elements in the power set? Power set, remember, is the set of all subsets of a set. So let this be the subset that you're forming. Now, here's your first element of big C. Now you have 2 choices. You're going to put it in that subset or not. Okay? So there's 2 choices for that, doing that. And then for the second element, you're going to put it in the subset or not. So you have 2 choices there. So for the first 2 elements, you have 4 choices. Right? It's, for example, it's in the subset, it's not in the subset. It's not in the subset, it's not in the subset. It's in the subset, it's in the subset. It's in the subset, it's not in the subset. So there's four ways. And for the third element, you can put it in the subset or not. So now you've got eight possible ways of for these 3. And then the fourth, again, 2 possible ways. So it's now 2 to the 4th. Now if you have little c elements, you're going to have 2 to the c possible ways of putting these into the subset or not. So the answer is the superset. 2 to the c, big C. 2 to the big C is 2 to the little c. Right? Hope you followed that. Alright, now that's with sets. Now a question on graphs. Let's read it out. Consider the undirected graph G, which is VE, where V is the set of nodes is 1, 2, 3, 4. Okay, so you have a graph with 4 nodes labeled 1, 2, 3, 4. And E, the set of edges, is, and then you're given a list. Draw the graph. Okay? So that's what the question's about. What is the degree of node 1 with node 3? Indicate a path from node 3 to node 4 on your drawing of G. Okay, so there's a multi-part question there. So let's the set of vertices, the set of edges, right? VE, which you're used to, and V is the set of your nodes or vertices, same thing. Right? And the edges are, now you're given a list. I'll write them out now. So here's, now it's the question says it's an undirected graph. Okay, so no arrows. It's not directed. It's an undirected graph. So here are the list of edges. So 1 to 2, 2 to 3, 2 to 4, or 2, 4. I mean, it's equally valid for 2. It's undirected. Okay? And 1, 4. 1, 4. Let's just check that. 1, 2, 3, 4, 5. 1, 2. Ooh, I've missed one. So it pays to check. 1, 2, 2, 3, yes. 1, 3. I missed that out. 1, 3. Okay, so 1, 3, 2, 4, and 4. Draw the graph. Okay, so draw, let's say, the 4 nodes. Now 1 and 2 are connected, 2 and 3 are connected, 1 and 3 are connected, 2 and 4 are connected, and 1 and 4 are connected. Right? So it sort of looks like a table with supports. Okay, draw the graph. So we've drawn the graph. What is the degree of node 1? Remember what that means? The degree of a node? It's the number of edges that connect to it. Right? Well, the degree of node 1 is obviously 3. Right? You can see 3 edges connecting to a node 1. What's the degree of node 3? Well, 2. Right? There's two edges connect to node 3. Right? Indicate a path from node 3 to node 4. A path from 3 to 4. A path. Just one. Indicate a path from node 3 to node 4. So from here to here. Well, there's that one. There's that one. There's that one. There's 3 possibilities. There's 3 paths from 3 to 4, right? Indicate a path, so you really only have to show one. That's what the question's asking. You read the question, right? Indicate a path from node 3 to node 4 on your drawing G. Alright, well, just do that, right? But you have to do it on your drawing. Okay, now those questions were from a section called exercises. And now I'll do one question. I'll mention. I won't do, but I'll just mention. These questions differ in level of difficulty. I mean, this one's pretty easy. Here's one that's much more open-ended. I won't do it. I'll just mention it. Okay, it's question 7 in the exercises. For each part, and there are 3 parts, A, B, C. Give a relation that satisfies the condition. Okay, so A, the relation is reflexive and symmetric, but not transitive. Right? So that's a sort of open-ended, creative type question that you have to find. And 7B is the relation is reflexive and transitive, but not symmetric. And part C, 7C, the relation is symmetric and transitive, but not reflexive. Okay, so I'll leave some of the more challenging ones for you to do. Okay, now the problems part, they're the tougher ones. Now, one that stopped me in my tracks was question 12, the problem section. Show that every graph, so you're asking for proof here, show that every graph with 2 or more nodes contains 2 nodes that have equal degrees. Okay, I'll say it again. Show that every graph with 2 or more nodes contains 2 nodes that have equal degrees. Okay, so when you confronted with a question like that, presumably you're asked, that's how I interpret it, you asked for proof. So, often the hardest thing in coming up with a proof is knowing where to start. How do you start? So, would this be a proof by contradiction? Would it be a proof by induction? By construction? Hardly construction, because you can eliminate that, because you're talking about every graph, right? So there's infinite number of graphs, so you can't construct it, I guess. So how about by contradiction? So could you assume, so your assumption, so you're trying to prove P, this statement, show that every graph with 2 or more nodes contains 2 nodes that have equal degrees. So that would be your statement P that you're trying to prove. So if you're going to use proof by contradiction, you assume the opposite, right? The contrary, the contradiction. So you assume not P, and what does that mean? Well, that means that every node has a degree that's different. Okay? Now if that's true, what can you conclude? Well, that's up to you, right? So that might be one approach. Another approach is by induction. So you assume that it's true for all graphs of size little n, let's say, And then you would try to prove that if that's true, then it's also true for all graphs of size n plus 1. That might be an approach you might take. And now that's the inductive step. Now for the basis step, with 2 or more nodes, so just say 2 nodes. So 2 nodes, therefore one edge, and the degree of those 2 nodes is 1 each, hence they're equal. So it's true for 2 nodes. Okay. So that might be a way to go. So like I say, theorem proving is an art, right? It's not easy. So yeah, I've given you some hints for question problem 12. Yeah, have a crack at it. See what you can come up with. All right. Now I'll solve problem 14. It was about the mortgage payment problems. Right? So you're to use theorem 25. What was that? Here's theorem 25. Remember from the lectures, gave you a formula for the size of your debt remaining after T months, after you've made T payments, right? And the formula is this. So P of T, that's the size of your debt,